So our first section is section 6.4, which is over arc lengths. Okay, so what I mean by arc length is, like, if I have some curve, I'm trying to figure out, like, the length of the arc of that curve. So let me give you an example. Like, if I had the function square root 1 minus x squared, let's say on the interval from 0 to 1, and I wanted to find the arc length. So we'll start by graphing it and just kind of seeing what this curve would look like. We've looked at this curve before when we were first starting to look at areas. We looked at the area under this function. Okay, so this is the unit circle, but in the case from 0 to 1, it's just in the first quadrant. So we have unit circle in the first quadrant, so it comes out to 1 here. And notice when I plug in 1 for x, I get 0. When I plug in 0 for x, I get 1. And then every other point in between gets satisfied with the Pythagorean theorem, x squared plus y squared equals 1 squared, creating this circle of radius 1. Okay, so if I wanted to find the arc length, that is, imagine that you were like this thing's really big. Imagine that you're standing right here on this point. We're trying to figure out how far would we walk if we walked along this path to get to this end point. Okay, so that's what the arc length is, just the length of that arc. One way that you can approximate an arc length is you can take like a piece of string, something that doesn't have stretch to it. Take a piece of string, lay it down over the curve, and then you can straighten it out and then measure the length of the string. Okay, so that's what we're trying to figure out is the arc length. Now, I really don't need any integration or anything like that to find the arc length of this particular shape, because this is a circle. And what is the arc length of a circle? Or what's another way of like there's another word for arc length specific to a circle? Circumference. So if I look at the circumference of a circle, of an entire circle, you guys remember the formula for that? We used it in the cylindrical shell method, 2 pi r. Okay, so this is the formula for the circumference of a circle. In this case, the radius is 1, but I'm also only looking at a quarter of the circle. So here my arc length, which I'm going to go ahead and call capital L throughout this, is going to be 1/4 of 2 pi times 1. So my arc length is pi over 2, which is, if you could get a decimal if you wanted to, pi over 2, it's about 1.57. Okay, so that means if you were standing right here on a circle, and you were to walk from here to here, you would walk 1.57 units, whatever the units are. If this is 1 foot and this is 1 foot, then you would walk 1.57 feet to get to here. Okay. All right, so in this particular case, we had this nice geometric function that we could just use a known geometric formula to find the arc length. But we're going to take a look at some other functions where we might need to use a different technique to find the arc length. Yeah, Amar? Yeah, the 1/4 came from the circumference of a circle is talking about the entire circle, right? So if I just did 2 pi r, I would get this entire unit circle. Yeah. Exactly, and out of all the 4 quadrants, I just want this first quadrant, so that would represent a quarter of the total circumference. Yep. So let's go ahead and do, I'll just go ahead and write out example 1. Find the arc length of the function on the given interval. Okay, so let's start off with the function x squared on the interval from 0 to 2. Okay, So let's go ahead and draw it so we can get an idea of what the arc length is going to look like. I'm just going to draw x squared from 0 to 2. So I need to go up to 4 then. And 1 squared is 1, 2 squared is 4. Okay, so there's x squared on the interval from 0 to 2. So we're basically trying to find, if you were standing right here and you were to walk along this path based off of x squared to the end point, what distance would you end up walking? That's the arc length. Now, we could get kind of a approximation for this arc length. Remember, that's kind of how we started with finding areas, as we were looking at just kind of approximations of the areas and then trying to put more and more things in there. So if I were to go from this point to this point just with a straight line, okay, now if I find the length of this line, is this going to be an under approximation or an over approximation to the actual distance? What do you think? So the distance of the line should end up being smaller, right, than the actual distance, because the shortest distance from one point to another is a straight line, and then we're deviating from that. So this arc length should end up being a little bit longer. I'm going to go ahead and call this L sub 1, because we're going to use another one later on. Okay, let's just find what the arc length is of this, and that'll give us an approximation of it. So notice what we could use is the Pythagorean theorem, because I know that this side length is 4, and this side length is 2, and it's a right triangle. So using the Pythagorean theorem, I have that this side squared equals 2 squared plus 4 squared. So L1 is the square root of 4 plus 16, which is 20. If you wanted to, you could simplify the square root of 20, because 20 is 4 times 5. So this could be written as 2 root 5. And either one of those is about 4.472. Okay, so 4.472, about a little under 4.5, would be the distance to travel from this point to this point directly. Okay, so this is an under approximation to the actual arc length of the curve. How are we doing so far? Okay, now just like when we were finding areas, if I put more rectangles into the curve, I get a better approximation. So if I want to put more lines under this, not under it, but just more lines to connect, like for example, I could take this point right here, and I could look at the arc length from here to here, and the arc length from here to here. Do you guys agree that that would be a better approximation? Like significantly better. Okay, so let's take a look. Now I have two triangles to find the basically the hypotenuse of. So this has a base of 1 and a height of 1, and so I could figure out what that would be. Well, it would be the square, right? It'd be the square root of these sides squared, just like this one was. It'd be the square root of a squared plus b squared. So the square root of 1 squared plus 1 squared would be the square root of 2. This one would end up being, let's see. So notice that this one has a base of 1 also. What's its height? It goes from 1 up to 4. So it has a height of 3. So this arc length, this hypotenuse length, is going to be the square root of 1 squared plus 3 squared, which would be 10. Okay, so that means that the other, using like 2 lines, I'll say, the approximate arc length would be the square root of 2 plus the square root of 10, which is about 4.576. this is still an under approximation. Okay, but notice, you see how when we used 2 lines, we ended up increasing our arc length? Okay, because this would be a longer distance to travel than just this one straight line. You see how I could keep going with this idea? I could use like 4 lines, I could use 8 lines, I could use 20 lines, just as many lines as I possibly could to get a better approximation. But as with the triangle or the rectangles, there's going to be a better way of doing this than just trying to approximate it every time. So let's see if we can come up with a general formula for arc length that we can use. Okay, so let's say that we had some curve. I'm going to kind of generalize this a little bit. Okay, so let's say I have some curve that looks like this. I'll call this f of x. And I want to find the arc length on the interval from a to b. Okay, so what I'd want to do is try to put in as many lines connecting these as I possibly could. Let's just pick 2 random points on here to connect with a line. I kind of like this color. Okay, so there's one line. I'm going to zoom in a little bit. So imagine that I had like a bunch of points in here, and they're all connected by a line, and I'm trying to find the length of each of those lines and then add them all together. Hey, Barath and Sean, can you guys? Thank you. So let's say that this one was x1 and this one's x2. And I'm trying to figure out what the length of this line would be based on just those 2 points. But we're going to imagine that we have a bunch of them in there. Okay, so this would be my triangle, my right triangle that would be represented. I'm trying to figure out basically what the arc length of just that piece is. So I'm just going to call this L for right now. Okay, so this distance is basically some change in the x coordinate. This distance is some change in the y coordinate. So to find the arc length, using the Pythagorean theorem, the arc length squared would be whatever delta x squared is plus whatever delta y squared is. And then we could solve for L by square rooting both sides. Okay, again, this is just one representative rectangle. We would want to have a bunch of these in here. Okay, are we all seeing okay that that's how we would get the arc length? We just have to figure out what's the base of the rectangle, what's the height of the rectangle, use the Pythagorean theorem. Okay, I'm trying to generalize this as much as I can. So the base is just some horizontal change, which is we've been calling delta x, and the height of the rectangle is some vertical change, which we've been calling delta y. Okay, so here we have this. Now what we're going to try to do is try to manipulate this to try to get it in terms of x only. Try to get in terms of x only. Okay, the reason why we want to do this is, are we seeing why integration might be helpful in this particular case? We're wanting to put a bunch of lines in here and then add up all of the lengths. That's exactly what integration does. It adds up whatever we need. Remember the integral sign, the elongated s, stands for sum. So we're going to try to, eventually we're going to integrate this because we want to add up all of these little lengths. In order to make these all become really little, we need delta x to become as small as possible. Okay, so we'll use that in just a little bit. Zoom out a little bit. Okay, but first I would like to try to manipulate this so it's not in terms of both y and x, so that it's just in terms of y instead, or just in terms of x instead. So one way that we can do that is if I factor out a delta x squared. Okay, so I'm going to basically factor a delta x squared out of this sum. If I take a delta x squared out of a delta x squared, I'd be left with a 1. If I take it away from this, do you see how there isn't a delta x squared in this one? It's just a delta y squared. So if I were to think about it this way, like if I were to distribute this through, I would want to get the delta y squared back, which means that what would have to go here is delta y squared divided by delta x squared. Okay, and it's totally fine if you're looking at this going, why the heck is she doing that? That seems weird to me. There's a few reasons why. I'll explain it more once we get towards the end, like why we would want to use this particular technique. It's okay if it's not feeling real intuitive right now. So one nice thing about pulling out this delta x squared is that that creates a product, which with square roots, when I square root a product, I can square root the first thing and then times square rooting the second thing. So this could be the square root of delta x squared. So you see how that would just be delta x times the square root of 1 plus this delta y over delta x squared. Okay, I'm just going to rearrange this slightly, and we're going to make this the square root of 1 plus delta y over delta x squared times delta x, like that. Now I just want to show you like what this equation represents here, okay? Because we could use this in a previous one that we did earlier, like this arc length, for example. So in the previous example, we looked at L1, right? In L1, delta x was 2, right? That was this pink one here. Delta x was 2. What was delta y? 4. So notice if I were to plug it into this formula, I would get that L1 is the square root of 1 plus delta x over delta y squared times delta x. 4 halves is 2. 2 squared is 4, plus 1 is 5. You guys see how we're getting 2 root 5? That same thing? Okay, so this is basically just the Pythagorean theorem, just written slightly differently. Okay, and the reason why we're writing it slightly differently is because as delta x goes to 0, then delta y over delta x becomes, well, let's think about that. As these 2 points kind of come in, the change in y over change in x would end up approaching the derivative, right? Change in y over change in x is slope. This represents the slope of this line, delta y over delta x, right? And remember that if it's delta y over delta x, that's a secant line. But as the 2 points become closer and closer to one another, that becomes a tangent line. So delta y over delta x is going to become dy dx, which is really the derivative at that point. And then this delta x, as they become, as this interval becomes shorter and shorter, that's going to become like the dx part of our integration. So remember, as we make the lengths of the rectangle smaller and smaller, as delta x goes to 0, it becomes a dx instead of a delta x. So this means then that our arc length is going, so this is the arc length of one particular, just one particular piece, not the arc length of the total thing. The arc length of the total thing would be the sum of all of those little arc lengths. So we're using integration to get that sum. We're integrating from a to b of the square root of 1 plus. Now, because I'm integrating, that means now all of those widths are becoming super, super small, becoming 0. That makes this delta y over delta x becoming the derivative. And then my delta x becomes a dx. So this is the arc length formula. In a testing situation, I would go ahead and give you guys this formula. Okay, if I said find the arc length, here's the arc length formula, you can use it. I realize the derivation of it isn't the most intuitive thing, but it's really just a version of the Pythagorean theorem. And again, the reason why this becomes f prime of x as opposed to delta y over delta x is because as these become smaller and smaller, the slope of this line becomes the derivative, the slope of the tangent line. And this allows me to write it just in terms of x instead of having x and y. So let's go ahead and use this now that we have the formula. So we're going to again keep going with the x squared on the interval from 0 to 2. So the arc length would be 0 to 2, square root of 1 plus the derivative squared dx. So our function was x squared. What's its derivative? 2x. Okay, so that's what's going to go here. It's 2x. And then I have the integral from 0 to 2, square root of, so this would be 1 plus 4, 2 squared is 4, so 4x squared dx. So this integral represents the arc length of the function x squared on the interval from 0 to 2. Okay, the reason why this is important is because if I had written this, what does this integral represent? The area under x squared on the interval. So this represents the area under f of x equals x squared on 0 to 2. Those are two very different things, aren't they? An area and an arc length. Okay, so our usual integral, that gives you the area, one thing we've been looking at a lot. This formula will give you the arc length of the curve on that particular interval. Okay, now this integral is not super easy to evaluate. So we have a few options. One thing we could do is we could use, we could use one of our approximation techniques to approximate this integral. Okay, so remember that the approximation techniques, like Simpson's, trapezoid midpoint, all of those ones, those approximate areas under curves, don't they? Okay, this is going to seem a little bit weird, but basically the area under this curve, the area under, I'll call it g of x because we already used f of x. The area under this curve on the interval from 0 to 2 represents the arc length of the function x squared on 0 to 2. Does that make sense? Like, because this is an integral, if I think about this representing the area under this curve from 0 to 2, that area, that number, also represents the arc length of this curve on the interval from 0 to 2. Okay. So if I wanted to approximate, let's go ahead and approximate L using, let's use Simpson's with four subintervals. Okay, this will be good practice back to Simpson's. Okay, so I already said g of x is the square root of 1 plus 4x squared. Okay, and we're looking on the interval from 0 to 2. Okay, so we're looking for the area under this curve, because that represents the arc length of the x squared curve on that same interval. So let's go ahead and divide 0 to 2 up into 4 subintervals. Okay, so my delta x is going to be 1/2. So S4 is going to be, how do I start Simpsons? What goes first? 1/3. Remember, the 1/3 is that weighted average between the midpoint and the trapezoid. Then my delta x, which is 1/2. And then what's my pattern? 1, 4, 2, 4, 2, 4, 2, 4, ends in 1. Okay. Notice I picked an even number. It has to be even. So I'm going to have basically f of 0 is going to be, or sorry, g of 0. You see why I wouldn't want to put f of 0 here? My f function is x squared. I'm not trying to find the area under x squared. I'm trying to find the arc length of x squared, which is given by the area under this curve. So g of 0 plus 4g of 1/2 plus 2g of 1 plus 4g of 3/2 plus 1g of 2. Okay, and so this is 1/6. G of 0 would be the square root of 1, which is 1. And then, let's see, 1/2 squared is 1/4. 4 times 1/4 is 1. 1 plus 1 is 2. I don't know why I made my root so big. Okay, plus 2, and then g of 1 would be the square root of 5. G of 3/2. 3/2 squared would be 9/4. 9/4 times 4 is 9. 9 plus 1 is 10. And then g of 2 would be the square root of 2 squared is 4, 16 plus 1, 17. You could also use the define in your TI-89 if you have that, and then you could just type it in from here. Okay, so we have 1/6, 1 plus 4 root 2 plus 2 root 5 plus 4 root 10 plus root 17. Okay, and when I put that into my calculator, I get about 4.6502, which notice is somewhat similar to my previous. This is when I used those 2 lines to approximate the arc length. I got about 4.576. Okay, so notice this is larger, so this is a closer approximation than just using those 2 lines. The actual arc length, if I use my calculator to approximate the integral, F3, integrate, so I want square root 1 plus 4x squared, comma x, comma 0, comma 2, is about 4.6468 if I'm going out to 4 decimal places. Okay, so using 4 Simpsons it got us accurate to only a tenth, but if we wanted more accuracy, we could use more subintervals. Okay. Let's do one more example. Okay, this will be B. Let's take a look at the function negative 2x plus 4 on the interval from 0 to 1. And let's just start by using the formula. So L equals the integral from a to b, so 0 to 1, of the square root of, now 1 plus the derivative squared needs to go here. So my function is negative 2x plus 4. The derivative would be negative 2. Okay, so then I'm going to square the derivative. Okay, so this is the derivative. It's just a constant, negative 2. Okay, so I have the integral from 0 to 1 of the square root. Well, negative 2 squared is 4. 4 plus 1 is 5. I have root 5 dx. Now we've got to think about what the antiderivative of that is. Okay, to kind of think about that, what would be the antiderivative of, like, 7 dx? 7x, right? The reason I'm doing that is some people get tripped up with the square root of 5 part. Just remember, square root of 5 is just a constant, right? Just like 7 is. The antiderivative of 7 is 7x. The antiderivative of root 5 is root 5x. I'm evaluating that from 0 to 1. And we plug in 1 minus plugging in 0. Plugging in 1 is just 1. Plugging in 0 is 0. So we are told then that the arc length of this is square root of 5. Now let's see if we could check our answer on this one. Because if I were to graph this, what would it look like? It'd be a line. I really don't need to use integration to find the arc length of a line, right? But this is a good way of checking our answer geometrically. So if I graph negative 2x plus 4, here's 4, and then here's 1. So it would be at 0, it would be 4. At 1, it would be 2. So we're basically trying to find the length of that line. This is 2. Okay, so notice if we use the Pythagorean theorem, I have the base is 1, The height is 4 minus 2 is 2. So this arc length then would be the square root of 2 squared plus 1 squared, which is the square root of 5. Obviously, this was easier, but it's always nice when you can use the integration formula and you get the same thing. Now, most of the time when we use this formula, it does not present very nice integrals as far as like using techniques that we've learned. So most of the time you will either find the integral that represents the arc length, and then either use your calculator to evaluate it, or use one of the approximation techniques that we learned to approximate it. Okay. But that's the idea here, arc length. Question?